Alright, so just a quick recap, announcement that there will be no lecture on next Wednesday. Alright, because I'll be on conference. And the lecture, there will be a makeup on the 24th. Okay, so there are no lectures next Wednesday. Alright, so don't wait for my lecture next Wednesday. Yes. The subsequent lecture will be on the 18th of November, so the week after this. Okay, I'll be going to Japan. But it's just for business, so don't ask me to buy anything. Banana cake. Strange, someone was asking me to buy a rice cooker. Okay, good. Alright, just a very quick recap, because as I said, there are three parts of this course, right? The first part, I don't repeat myself again, but sensitivity, okay, and ability margins. That's the first part. Second part is home placement, PID, controller. That is the last part. And it's the part that you'll be most unfamiliar with. Alright, so please pay special attention. There's also a reason why I want to do a quick recap. Alright, I'm not going to bore you to that, but it will be quick and simple. So for every state space model, we look at the always states. Okay, states can be angle, okay, we have change of angle. Alright, so every time when you have states, of course there have to be dynamics, so that the differential equation, something like this. Okay? And the state space model is always this. X dot equals to x plus bu, and y is cs plus bu. Okay, usually for the output, we are mostly concerned with one output, but we may have two outputs, alright? So if C is 1, 0, alright, because y is cx plus 0u, alright, usually that's the case. If y is cx and c is 1, 0, then 1 times theta dot plus 0 times theta, the y is theta dot. Alright? Okay? And because of transfer function, alright, you need to know how to derive this. GS is C, open bracket Si minus A, bracket inverse B. So I've gone through this many times. Okay, for closed loop transfer function, instead of A, we have A minus BK. Okay? Alright, instead of A, we have A minus BK. And there's no B. Because for closed loop transfer function, we say that U, okay, for state feedback control, U is minus KX. Alright, so effectively, the X dot is AX minus BKX. And group that together, this here is A minus okay? Dynamic behavior is one thing that you ought to know. We have gone through this times. When you look at dynamic behavior of the closed loop system, we look at the poles of the transfer function. And what are the poles of the transfer function? We are the determinant of Si minus A minus B. Okay? And we are looking at the eigenvalues A minus B. Alright? This is something that is very important because year on year we always ask, we illustrate the concept of state feedback using a block diagram. So you need to draw this for us and X is a concept. Okay, double line. Alright, the other thing is the definition of controllability, reachability, observability, detectability. We'll emphasize this last lecture, we have a copy, right? Okay, when we talk about the controllability matrix, gamma C, BAB, all the way to A power 10 minus 1B. Okay, and we said that it's completely controllable if your controllability matrix is full row rank, meaning the rows are independent. Okay, observable, we have two forms, controllable canonical form and observer canonical form. So how to design a controller, you put the system into controller canonical form. How to design observer, you put the system into observer canonical form. Alright? And usually what we'll give you is either the transfer function or we can give you a differential. Alright, so if we give you a transfer function, the least you should remember is how to convert from a transfer function into a controller canonical form. If you can't remember this, there's nothing I can do to help you. Okay, so just arrange the coefficients from the left hand side to the right hand side in this manner. The bottom is a triangular matrix. And S is, the back S runs through. Okay? B is 1, always the case, because we are looking at only one most of the time. Okay, C is, if we arrange the coefficients from 1 to n in this manner, D is usually 0. Alright? What about observable canonical form? If you cannot remember so many, just note that we say a duality theorem, GS is GS transpose. GS is just transfer function, it's a polynomial, so it's a scalar. Okay, by this, we know that, okay, the observability matrix will just be a controllability matrix transpose. Okay, the B will be the C transpose on the controllability matrix. The C will be B transpose on the controllable canonical form matrix. D will just be B transpose. Okay, because canonical controller, canonical form, and the observer, canonical form, they share the same transfer function. They're the same system, just that you represent them in two different ways. Okay, so just remember the controller canonical form, and remember this, you can write the observable canonical form. Alright? Okay, so that's just a quick recap. The other thing I want to point you to is tutorial. Not important. Some of the questions are what you will see in the exam. Okay, so take note that now you can at least do 1 to 7. Okay? What I'm going to do is, after we finish, we'll have a bit more focus. I'm not going to do half and the other half later. Okay, I'll run through this tutorial. Okay, but just highlighting this to you so you can try. Okay, so we finish the lecture on this page, then we'll come back to it. Alright? Okay, any questions? Good. Just to show you, give you a flavor of a question on state space. So this is from last year. So they could ask, like, first of all, describe the concept of state feedback control using a book diagram and derive the differential equation of the closed system. So this is what it's done for us. Actually, you cannot see, but there are numbers. It's quite big, right? And the differential equation. And just take feedback control. Okay, without the copy, we'll go through this in the revision lectures. Alright, and we can also ask you, like, for the state feedback system, what's the controller designed by co-assignment? And how can we use to describe the state feedback controller? Okay, this is the tutorial. Alright? Design a state feedback controller K for this state space using pole placement the way that it gets overshoot at right hand. So this is what we're going to cover for today. Okay, how to do pole placement for state space. Alright? And we're also going to cover this. Your reference input show how the state can be divided. Alright, so this would be a typical state space question for the exam. Okay, so without any further ado, alright, so we begin our lecture today of state space pole placement design. Among the star must know how to draw. Okay, must, alright? So double line for vector will be K. Okay? The state space model is x dot equals s plus du. Okay, y is c times x. And we usually assume d is 0. Because y is cf plus du, right? Because this is state feedback control, so we feedback the states with a negative state feedback k. Okay, so the states, double line for vector. K, which is a matrix, has a negative sign. So U equals to minus kx. Alright, so U is minus kx. Okay? Alright? You put your system in controller canonical form. Alright, for such a transfer function. That's a copy this. Don't use this one. Alright? What is more important is the next slide. Okay, so how do you do state feedback control? Alright, so you know the x dot is gas plus du. Right? U equals to minus kx, so the control input is negative k times x. So with the substitute u equals to minus kx, then I have ax minus bkx. Okay? And you group x together, then I have bracket a minus bk equals bracket x. Alright, you know a. Okay? Wider.
That screen is not more.
Okay, you know how it's sometimes good spoil. Okay? Is it coming on? Is it coming on? No. Okay, this one I'm going to do. I'm going to zoom in all the way just like that. Do you see this? On the back? See? Very big. On the back, I don't see. Here, those at the back, if you want to, there are a lot of seats here. Seriously. One sheep in front. No? Okay? So you know A, right? The next question is how do you form B A? So you take B, 1, 0, 0, 0 all the way. K is a gain vector. Because you need K times X. So according to the order of X, you have about the order of K, right? So assuming that this is n order, so the K1, K2 all the way to the n. The K1, K2 and Kn, they are all scalars, they are all numbers. Okay? So we take B times K, and now we K1, K2 all the way to the n, and triangular all equals 0, whether it's all 0. Diagram of 10 by n meters. Okay, next is take A minus BK. For A minus BK, you have negative bracket AL1 plus A1, negative A2 plus A2, negative plus A. Alright, and the triangular matrix factor. And brackets. And the monitors still off to the back. Yes. We will hang on for a while. I think about another 10 minutes maybe. We'll take a 5 minutes break and then I'll just restart. Huh? Okay? Alright? I think there are not so many words, so we shouldn't have too much of an issue. Okay? Alright, so let's move on. Okay, so for state feedback control, we said that it is known that a system which is fully controllable, we have a controllability matrix, which is full row rank, non-singular. Alright, and such a system can be transformed into a controller in the form. And you can use full state feedback using u equals to minus ax. So basically what we do is we move, okay, from previously a open loop system. So previously look at A alone. Now I look at A minus BK. Okay? And A minus BK, you move the values from A, right? The minus A1 all the way to minus AN, we move them from minus A1 to minus AN to minus bracket A1 plus A1, minus A2 plus A2 all the way to minus AN plus AN. Alright? So very straightforward. Okay, this particular slide, you change from this to this. And this slide is very important, so you can write down this question because it will always come up most of the time. The question is, star here, describe how pole assignment is used to design a controller in state feedback. A, describe how pole assignment is used to design a controller in state feedback. Alright, this is wrong. So strike it away, change it to this. Okay? And you ought to know how to derive from open loop GS into this GS format in state space. And remember, I was showing you the exam question for last year. Describe how feedback, blah, blah. So answer is on this slide. And the next one. If I were going through, we'll go through the solution on the revision. Alright, done? No. Okay, for those at the back who cannot see, the question is describe how pole assignment is used to design a controller in state feedback. Okay, so those who are done, what I'm writing here is, because you're doing state feedback control, right? So U is minus AX. And the closed loop transfer function, GS, will then be C bracket SI minus bracket A minus BK, close, inverse, and C. Okay, what is there, B there? Is this supposed to be a B? Because it's X0, right?
Choose K so that you can place the poles at decimal location.
Yes. Last few words, where? Choose K so that you can place the poles at desired locations. Yes. Is that what you want to ask? Sorry, the words are this one.
I thought it's decimal.
Please, sorry, there's no here. Yeah, my apologies, because sometimes my handwriting is quite bad. Okay, so that's asking. Alright, for those at the back who cannot see, choose K so that I can place the poles at desired locations. Okay, this is just an explanation. Alright, what is the answer that we are looking for when we ask you to describe? Okay, so the answer that we are looking for is that by state feedback control, alright, we move, the location of the poles or the eigenvalues of the state matrix A, which defines the dynamic behavior of the system, to, the eigenvalues of the matrix A minus BK. Alright? So, by modifying the eigenvalues of A minus BK using state feedback, we can change the location of the poles and eigenvalues, and we can change the dynamic behavior of the system. Okay? Alright, by changing the location of the poles or eigenvalues from a state matrix A into the poles and location of the eigenvalues in the state matrix A minus Bk by the state feedback gain K, okay? We can change the location of the poles and eigenvalues and hence the dynamic behavior of the system. Alright, is that all? No. Okay, so you say this, and then how do you do that? Alright? The next part of the solution, okay, is the system has to be completely controllable. Alright? And hence we can arbitrarily assign the closed loop poles of the system by feeding back the state through a suitably chosen gain vector K. Alright, so you said that you change from eigenvalues of A into the eigenvalues of A minus Bk. How do you do that? You select a suitable constant gain vector K that can place the closed loop poles of the system in arbitrarily assigned desired locations. Alright? Okay, we'll go through, so if you're interested, I'll show you the answer that we're looking for. I don't have to copy because we'll go through it again, right? So the answer is by modifying the values of the state matrix, which is A. Using state feedback, you can change the location and dynamic behavior system. Okay, A minus Bk, we call this closed loop assignment, and closed loop poles arbitrarily assigned the particular state back through a suitably chosen gain vector. Okay, exactly what is in these two slides. Okay, so that's why I label. If you have been attentive, I label this slide 1, circle, half of the answer, 2, circle, the other half of the answer. Okay? Alright, so that's the theory. Okay, now with 1 circle, 2 circle, yes? Example, for assignment, example. So if you have a transfer function, GS, which is a polynomial transfer function, 2 over s squared plus 7s plus 12. Okay? We call the controller canonical form because now we're designing a controller for assignment. Yeah? So from this transfer function, put it into state matrix. Okay, for those who cannot see, let me just zoom in. Apologies to those in front. Once you finish with this example, we'll take a 5 minutes break and I try to fix the thing behind. Yeah? Okay, so this is your transfer function, right? Can you tell me what is Bn? Bn is 2. Okay? Alright? So your C, the C matrix will be 0, 2. This is second order, right? So B2 is 2. Okay? S to the power of n, s squared, so n is 2. So what is A1? A1 is 7. Yeah? What is A2? The back is 12. Okay? Honestly, you don't have to copy this as well, because this is in the previous substeps. Alright? Okay, for those at the back, I'm just writing this so you don't have for this transfer function you put here. So you put this in the state matrix. Okay? So as I said, A1 is 7, so you have minus 7, minus A1. A2 is 12, so minus 12. And a triangular matrix, so 1, 0. B is always 1, 0. C, 0, 2. Okay? So you can write this as the first step. Subsequently, in your slides, we try to teach you how you can derive this in MATLAB. Okay? In MATLAB, we can do a lot of things. We can plot this plot, Verde plot. We can also do a lot of this in MATLAB, right? How to pole, assign pole. Okay, why is it important for us to just go through this? Is because if you have a question and you have tried to hand solve a solution, and if you have any doubts about whether this solution is correct, you go to MATLAB. Alright, so in MATLAB, what you do is you set up the system in the transfer function format, implement the display description, okay, verify the original codes of the system, that's a -4 and 3, enter some gains, so you can get close to location -10 and -20. Alright, so just, I don't know how important it is to go through this, because this is not what you're going to do in exam, you're on computer, right? Okay, but for your sake, you know, in future, if you have I don't know in future or now, whether you're trying to figure out whether cost for this, you can form the desired closed loop polynomial, s plus 10 plus s plus 20, because the desired close are -10 and -20, s squared plus 50s plus 200. The solution will give you automatically is 23 over 8. Okay? You can also check that you have this eigenvalue, a minus bk. It will tell you that now eigenvalues are at -10 and -20, which are the desired orientation. So how do you do this in calculation? So these are the steps. And this one I'm not because this is something you have to know before placement, right? This is what you will be tested in your exam. Okay, so for this example, first of all, what you do is you form your desired closed loop polynomial, ACL. Okay, so your closed loop poles are -10 and -20. Right, s plus 10 times s plus 20. So your desired closed loop polynomial is s squared plus 30s plus 200. Okay, next. Alright, what you do is you write down alpha c bracket a as a squared from s squared plus 30a, you replace your s by a, plus 200i. Okay, from this. So, before we continue, you want me to show you how you get this? Yes? Let me just cover this for a while. Too small, I will zoom out. Or zoom in. Okay? So A is okay? A is -7 minus 12.0, right? So in your equation, you are required to write down a squared plus 30a plus 200i. Wherever is a squared? A squared will be a times a. Okay? So for those who still cannot remember how to do the multiplication, -7 times -7. So it's 49. Okay? Plus -12 times 1, -12. -7 times -12, 84, plus -12 times 0, 0. Okay, 1 times -7 plus 0 times 1, 0. 1 times -12 plus 0 times 0, -12. Okay, you have 37, 84, -7, -12. Next, 38, so you take 30 times 8. So take 30 times each of these elements. So 30 times -7, -210. 30 times -12, -360. 30 times 1, 30. 30 times 0, 0. Okay? 200i. It's just 200 times 1001. Okay? 200 times 1, 200. 0 times 1 is 0. 0 times 200, 0. 200 times 1, 1. Okay? Add them up together. So we have a squared plus 30a plus 200i. Okay? And that gives you 27 minus 276 and 3 over 8. those of you who are still a bit rusty with your matrix multiplication, please go back and practice, alright? Okay, can I take this away? Yes? Can I finish copying? May I suggest you copy the answer, each of this, and then my answer. Yeah? I'm leaving this for me also because of this, especially as okay? Alright? Okay. Next, what you do is you form the controllability matrix VAB. This one of these are very much quite straightforward. And you find the inverse of controllability matrix like this. So how do you do the inverse of this? Okay, you have this diagonal elements, they will remain, right? And the cross diagonal, multiply by -1. So 0 plus 1 is 0, -7 plus 1 is 7. And the determinant of this is this times this minus this times this, right? So 1 plus 1 is 1, minus 0 plus 1 is 7. So the determinant is 1. This will divide so by 1 is the same. Know that? Okay? Alright? So by Ackermann's formula, we say that we can calculate the state feedback constant gain vector K using this formula. Second order, 0, 1. Inverse of controllability matrix times alpha C bracket E. Okay, so 0, 1. Gamma C inverse is this. Alpha C bracket A is this. You can compute when it's rewriting. Go back and this, alright? Okay, if you are just looking at me, there are a few ways of multiplying this. You can multiply this from the front, or you can multiply this from here and then you do this. Okay, so just to illustrate. Okay, so just to illustrate, what you can do is this. Okay, so you can combine these two at the back into this. Okay, and then do this multiply. Or you can combine these two in front and then multiply. Doesn't matter.
It's like a border actually.
Yeah, I leave it to you to see whichever is here.
Don't want that slash A bracket here. Bracket.
Right? Okay? So it doesn't matter which way. Alright? Okay, so the steps is this. For assignment.
You never copy up.
So usually the exam question asks you to check that gamma C is squirrel rank, controllability matrix is squirrel rank. Alright? To calculate the state feedback vector K, we form the desired closed loop polynomial, which is this. Transform the system into controller canonical form as compared elements of A, corresponding elements of ACL and elements of K. So this is the thing. Instead of doing this, you can so you get this. So you add this with the polynomial of Si minus A minus B. Okay, because the closed loop polynomial ACL is just the determinant of Si minus ACL, which is A minus B. theory. But instead of doing this, it requires 1 step, 2 step, 3 step, which is something that you never do in the exam. Okay? But this is the theory. So what is it that you do in the exam? Okay? What you do in the exam is this. Gamma C is full row rank. Sorry. Okay? What you do in the exam is this. You use the Ackermann's formula. And K is just 0, depending on the number of order. 1. Gamma C equals Gamma C K. Which is how we just got. Okay? So you just, this is what you do. Okay, start. Okay? And this is available in the lab. So if you have issues with your calculation, you can go to the lab and do this. Alright? Okay, so let's take a 5 minutes break. We'll come back at 2:15. Well, I have to fix